So this is based off of a question in the textbook, but I give you more explicit directions than the textbook gives you. So first I say take the natural log of the population and record it in the table. Okay, so I just pull out the calculator, and the population is in millions, but I don't care because I'm just chopping off zeros. It's not going to make any difference, right? So I can just say natural log. What I mean is it's not going to make any difference to the problem as long as we're consistent with what we're doing. Where is natural log? There it is. Natural log of 361 equals 5.8889. Okay, I'm going to pause while I fill in the table. Okay, because I'm very confident that you can click that into your calculator as well as I can. Next step says sketch the points in the grid below. So I'm going to take a copy of this chart down with me, but let me just see. The years are going to be 51, 61, 71, 81, 91, and 2001. I'm going to make that 101. So I'm going to take a copy. Okay, and I'm going to go down here to the grid. Go, and so there's a copy of this little chart over here so we can see it. Okay, there we go. So now we're going to have to figure out how to list the axes. So we want to usually put year down here and population over here. Okay, so usually horizontal is time or x, and usually vertical is whatever else there is. And I'm thinking, well, if I do every 2 blocks is 10 years, we're going to end really soon. But if I make every 4 blocks, I'm going to overrun. So I'll make it 3. So, and I have to just kind of experiment till I figure out what works. If this were an exam question and you picked to space these every 2 blocks, it would be totally fine. Okay. So let's see, now we need to figure out what the other axis is going to be. It should probably go from at least 5 to 7 or higher because, let's see, it's going to ask us to make a prediction for 2011. Oh, that's good because that's going to be somewhere over here. So let's see, it's probably, let's make it go from 5 to 10. How's that? So maybe if this is 5, and this is 10 roughly. How far apart does it count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Well, if I move this guy down to here, move that guy up to here, this is exactly 20 by 20. And so, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this looks like 7.5. How's that? Okay, I'm going to pause while I space this out better. Okay, so I mean, I'm just going to keep that spacing, but I just put the numbers in, so I'm going to get rid of that. So it's 0.25. Every block is 0.25. This is different from what I did on the answer key, and that's totally fine too. All right, so now I'm going to say what happens in year 1951. I'm going to try to put a point at about 5.9, maybe 6, because, I mean, what's the difference between 5.9 and 6 anyway? It's about the same. And then in 1961, well, okay, it's like 6.1. So it goes up a teeny bit. And then we have 6.3. Okay, so this would be 6.5. This is 6.25, so it's a little bit higher than 6.25. Let's see. 1981 would be 6.5. So it will be right here. There we go. 91, 6.75. It's really, really close to 6.75. So that would be right here. And then the next one's really close to 7. Okay, so we have some points here. And then it says, sketch an estimated line of best fit. So let me make a comment. If you've taken statistics, a line of best fit is defined in a very formal way. You're given a definition and you have to find all sorts of stuff, calculate it. But we're not doing linear regression here. What we're doing is, the point is, if you have a whole bunch of points that look like they're on a line, there's 1,000,001 ways of trying to figure out exactly what that line should be. Should it be here? Should it be like that? Should it be like that? Should it be like that? But all these lines that a normal person would try, they're all good enough. For the purposes of visual estimation, we just make a line that looks about right. And the deal is, the closer these points get to falling on an actual line, the less your model matters. I mean, if you have crazy points out like that, then your model matters a lot more. But these points, strangely enough, seem to really fall on a line. And so if they do fall very close to being on a line, any model is going to give you roughly the same answer. And so that's the theory behind this question, is that by some freak coincidence, these points do fall on a line, which means, or very close to falling on a line, which means the population of India over this time interval really is growing exponentially. Not just like everyone says, oh, it's growing exponentially, because lots of people say that and they don't really mean anything by it. But this is really what it's supposed to mean. And so let's go ahead and keep reading the question. Use the line to predict the population for 2011 by estimating a point, then figure out what the population would give you at that point. Okay, so I'm going to figure out, where is 2011? It is right about here. 2011, in other words, 111. Okay, so I'm going to just go up here and say it's about like that. This would be 7.25, maybe more than 2.5, but less than 5, maybe 7.35. Now, on the practice exam, I said 7.1 because I just drew a different best fit line that was still very close. But, you know, see, actually what happened is, I can tell you, this point I drew it too low, and that influenced the way I drew my best fit line. But that's okay. We're still in the right ballpark. Okay. So is equal to estimate for 2011. Great. Then it says figure out, oh wait, this is the estimate. Let's go back and figure out what we're saying. We're saying in this column, the natural log of the population is what is 7.35. So what would the population be? Aha. So I would have to say e to the 7.35 is equal to what? So e to the power of 7.35 equals 1556 million, which is the wrong units, which is really like 1.5 billion, okay, or 1.6 billion. All right, so we were talking 1.5 or 1.6 billion people in 2011. Okay. The actual 2011 population count was 1.2 billion. What does that do with relation to your model? Well, I'm on the high side, but in the right neighborhood. So you write something like that on your paper. Again, if you had, let's just take another color. If you had moved this point up a little bit, you might have been more tempted to draw your line like this, and you would have had a better estimate. But this is completely nuts. Why should this even be working? It's actually pretty crazy that any population that's naturally occurring is fitting the exponential model so closely. It's not like bacteria in a petri dish. So this is really quite crazy, I think. So Okay, I guess that's all I needed to say about that question.